Hello and welcome back to Calculus 1. This is section 4.2 on mean value theorem. And this is a very interesting section where we learn this concept which connects the world of average with the world of instantaneous. So to start things off, the average was the slope of the secant line, right? And that was f of b minus f of a divided by b minus a. And that was basically algebra. You have 2 points and you find the slope between those 2 points. Slope of the line that connects those 2 points. Now, the other concept which we learned in calculus was the concept of the derivative, which was instantaneous change. So instantaneous change was slope of the tangent line, which was the f prime of x, and that was given by the limit of f of x plus h minus f of x divided by h. Oh, h goes to 0. Forgot that. So today's section on 4.2 is going to connect these two concepts and allow us to understand the world in some sense. Now let's take a look at the situation here. Now usually when I teach this class in the classroom with 30 students sitting in the room, I ask, have you ever or have you know of anyone who received a speeding ticket in the mail without ever being pulled over? And usually someone would say yes. Now we're going to understand how that works. So first of all, when you are pulled over for speeding, your speed was measured, the instantaneous speed is measured, and you are quoted for the instantaneous speed. So if you were driving, let's say 80 on 65, that's 15 over, right? But it was that instant when you were driving 80 that got you pulled over. And at that instant, when you were measured using any of those speed detection units, right? You were clocked at 80 miles per hour in the instant you were measured. That's instantaneous change. And you are ticketed for that particular speed. Now, there is something else that can be done, and I'm going to draw that situation here. So let's say this is a highway. This is your car looking from above, right? Tires on the side over here a little bit. There we go. The posted speed limit, let's say it's 60 miles per hour. Let's say that's a posted speed limit. And let's also assume that you have one of those radar detectors so you would know when the speed trap is set. So this is some shrubbery. And behind, we're going to have a speed trap. There we go. By measuring right here, let's say. And you are driving, so your radar detector goes off. You know that there will be a speed trap, and what you do is you go through at 60 miles per hour, right, without being pulled over, because the limit is 60, you drove 60, so it's all good, you're not pulled over. Now, down the road, there's going to be another speed trap right here. Absolutely same situation. and you are going to drive through the second speed trap as well at 60, because again your radar detector goes off, and that's that. Now, these two speed traps are going to be, let's say, 5 miles apart. And then let's say that you went through the first speed trap at 1:39 p.m. and you went through the second speed trap at 1:43 p.m. So how come you received the ticket? You went through both speed traps at 60 and you were not pulled over at all. Now, in reality, this is not done with squad cars. This is done with those cameras and easy pass gates and so on. So now, what is happening here? Well, let's take a look at the average speed. So you are covering 5 miles in 4 minutes. Now, we convert those minutes into hours because we do not want minutes. When you cancel 4 and 60, you get 15. Cancel minutes and minutes. And you get 75 miles per hour. So from the time you were clocked on and the first speed trap, this timestamp of 1:39, and then the timestamp of 1:43 for the second speed trap is enough for officers to know that you were speeding in between the two, right? There is 5 miles of road in between. Now, as I mentioned at the beginning of the lecture, is that they always clock you for instantaneous, not the average speed. Because average is the average speed across the entire trip. And you are never observed for the entire trip. I mean, the squad car could be behind you for like 10 minutes or 2 minutes or whatever, but it's never going to be like an escort, right? From the moment you leave the house until you park, let's say at school. It's never that, the squad car is right behind you for the entire trip to take averages and things, right? So it's always this one short burst of measuring the speed, and then you are ticketed for that. So now what we calculated here is that the average speed is 75 miles per hour. Well, what we are learning with this mean value theorem is we are learning a theorem which tells us that under certain conditions, at least once, average speed and instantaneous speed is the same. And that theorem guarantees that your instantaneous speed was at least once 75. So solving this basic physics problem, right, where you have the distance traveled divided by time traveled, that's going to be giving you the average speed. Now we have the theorem which connects that average speed to the instantaneous speed and says, okay, you were at least driving once at 75, so we can issue the ticket for, in this case, right, 15 over the speed limit, because 60 to 75 is 15 over the speed limit. So now we need to take a look at this theorem, and then we'll go back to our problem and just claim this. So what does it say? So if function f of x is continuous on closed interval a, b, and differentiable, on open interval a, b, then there is at least one point C in AB such that f prime of C, which is the instantaneous world, is equal to f of B minus f of A divided by B minus A, which is the average world. This is your formula, and these are your conditions. Now, we don't do the proof for this in the what I call vanilla calculus class, right, which is this one. In honors course, obviously, we do the proof for the formula, and students are required to know it. In this class, we explain what this means and how it works. So the first, you see the two conditions, continuity and differentiability. Now, what does that mean for our word problem, right, of you driving down the highway? Well, first of all, it's a continuous trip. You are not teleporting across. I mean, even with teleporting, it still takes time, right? Information can travel at the speed of light. So if you're teleporting and turning your mass into electromagnetic waves and then turning it back later on, that will still take some time. But if you imagine that it's instantaneous teleport in some sense, right, then the trip would not be continuous. But since you have to pass through every single point of this road, your trip is continuous. And your position function, which measures how far you are from the, let's say, this 60 mile per hour sign, is a continuous function, and its derivative is called the velocity, and you are driving at some speed, so it's differentiable as well. So it does apply. In this case, your conditions are satisfied, right, of differentiability and continuity. And then, by this theorem, we can see that the 75 miles per hour that you had on the average is at least once 75 miles per hour on instantaneous side, which is the side you are getting ticketed for. Now, in more graphical terms here, to understand how this also works, is if you draw some function and you pick up values A and B, the black line you see there is the secant line, which contains slope m secant. Now, the derivative is the tangent line, and if the m tangent is equal to m secant, that means that the lines are parallel. That was the basic algebra idea. When the two slopes are the same, lines are parallel. So we are able to draw a parallel line to the line we have here and figure out this point C for where the m tangent will have the same value as m secant, meaning they are the same, which is the formula left equals right up there. And we see that that happens, right, at least once. So now that hopefully makes sense graphically when you are thinking about slopes, where one is the average change and the other one is instantaneous change. So now, when you look at this graph, right, you realize that you can have many of these depending on what the shape of the graph is. So now we can solve, just what I call boring problems, right? Where they just say find the value C, right? Use mean value theorem to find value C where the slopes are the same. Or you can have the word problems like the one that we had with the police trap. So now going back to this trap, this is easily achievable, right, and tested many times and used many times with easy pass gates, right? Because if the two easy pass gates are, let's say exactly 10 miles apart and the speed limit is 60, then your time is not supposed to be faster than 10 minutes. Now, it's not really practical to just rely on that, but in some sense, it does work. So if you have two gates 10 miles apart, then 0 to 10 minutes is 10 minutes is the lowest time you are allowed to have, so that the average is 60 miles per hour, because you're covering 1 mile per minute. 1 mile per minute is 60 miles per hour, because 60 miles in 60 minutes, 60 minutes in 1 hour, right? So the reason why you cannot just rely on easy pass gates and the cameras, in two locations separated 10 miles apart is because technically someone could drive double the speed limit, get to the second gate in 5 minutes, and then stay parked 5 minutes in front of that second gate and then pass right after 10 minutes is up. So you are not really saving on time, right? You're not paying the ticket either, but then there is that part where you drove 120 miles per hour in between the two gates where the speed limit was 60. So it can't be really just, okay, let's put the two easy pass gates and so on. So we still have that live monitoring. However, right, it does help on the long run. Now, again, the whole different debate on whether the speed limits are too low and, made just so people can pay fines and so on. And I'm definitely in that camp of speed limits are way too low on the highway. And, we have the example of Germany that has highways without the speed limit. So sure, it works just fine. But the thing is that in reality, you must have these 25 mile per hour speed limits and 30 speed limits in residential area, where at any point, a kid could run out in the street, after the ball or something, and the stopping distance when you are driving 60 miles per hour and 25 miles per hour is quite different. So as much as I am in favor of low speed limits in residential areas, I am definitely not in favor of any speed limits on highways. But again, that's a personal opinion, and that does nothing to do, right? Has nothing to do with the reality of mathematics and this theorem that it can be used. What happened?
We need an Autobahn.
That's the German, yes, that's the German highway that has no speed limit on it. Now you have different highways and different speed limits throughout the U.S. Clearly, I think was Georgia and South Carolina, I believe they have this highways where maximum speed limit is posted at 75 and minimum speed limit at 45. So you also have a minimum speed that you have to maintain, and you get ticketed if you are below that speed. That's another thing. Again, that all now boils down to policy and politics and all of that stuff, which we don't waste our time with in the class. Now we just want to understand the actual theorem and how these things come about for, let's say, ticketing the driver, right? Ticketing a driver who drove over the speed limit without being pulled over. And now you know, if you ever receive a ticket, how that ticket was generated, because you can only be ticketed by law for instantaneous speed. And this theorem connects the average and instantaneous. So now going back to these calculations, we can go and pick up one of the examples from homework and try to solve that one. There is also another thing in the book where they talk about something called the Rolle's theorem, and the Rolle's theorem is is a theorem that is used to prove the mean value theorem. And again, because we are not dealing with a proof, I skipped over the Rolle's theorem and went directly into the mean value theorem. Now, as I mentioned, you have two different types of problems. One of type is the boring ones, and the other type is the one where you solve the word problems. So now for the boring problem, they give you a function, they give you the interval, and they ask you to find the point C at which instantaneous equals the average. And usually I go over homework example 26, which gives you the function as ln 2x on the interval 1 to e. Now, you check ln x for continuity and differentiability on this interval. So when you look at this interval, your domain of ln x is 0 to infinity. Now you are on 1 to e, technically like 1 to 3 almost. The function is continuous on 1 to 3, ln, right? Function is continuous. And it's also differentiable in that interval. So both conditions are satisfied. So continuity, pass, differentiability, pass. And then you go and you can start computing. If you don't check conditions and you don't know that one of them failed, your calculation is garbage, because it has nothing to do with reality. The theorem fails to make the comparison between the two if any of the two conditions do not hold. So you must check conditions before you do it, which is why I say the calculation is garbage, because it's going to give you a number that has nothing to do with reality, right? You have to understand that, and it's very simple to understand it if you just look at 1 over x, right, and you pick 2 points like this to try and calculate the mean value theorem. This is not continuous, and because it's not continuous, there is no way to plug in a tangent line with the same slope anywhere, because none of this is a discontinuous function, and all of the slopes of the tangent line are negative. So you will be able to compute something, but that something will not have anything to do with reality. You absolutely must check conditions, and then you can go into calculation. So for my formula, f prime of c equals f of b minus f of a divided by b minus a. I have my a and b in the interval. I need to find the derivative. F prime of x is, this is ln, so you copy the function as is, and then you put the derivative like a chain rule right up there. They cancel, so you still get 1 over x in this derivative, which means that f prime of c is just 1 over c. and I will just plug everything in. So f prime of c is 1 over c, f of b, that's going to be ln of 2 times e minus ln of 2 times 1 divided by e minus 1. So we just plugged in all of the values. We plugged in a c into the derivative. We plugged in a and b where they belong in the functions there. And now we just need to work this out. Now, to solve this equation and calculate the value for c, you can use the ln rule, ln2 plus ln e minus ln2 divided by e minus 1. We know that the multiplication, right, turns into addition if you studied those formulas. These two cancel, and you get 1 over c equals ln e is 1, 1 over e minus 1. Now, when you flip both sides of the fraction, c equals e minus 1. And there it is. So that is the point. You can, go into a calculator, plug in e minus 1, get your decimals, about 1.7. And that would be the point at which your secant line and your tangent line, well, the tangent line at the point C and the secant line between 1 and E would be parallel lines. So you are able to find the location on x-axis that produces the same slope. So you're technically setting the slopes equal, and then you're working your ways backwards to find the value x at which the slope of the instantaneous, the slope of the tangent line, is the same as the slope of the average, which is the secant line. Now, for the word problem, they also have a couple of these problems in the mean value theorem. And I believe there should be a problem with the runner somewhere. There we go. 45. Explain why, if a runner completes a 6.2 mile race in 32 minutes, then he must have been running at exactly 11 miles per hour at least twice in a race. So that is, again, another problem that we have. So this runner is going to run 6.2 miles in 32 minutes. And that's the same information like we had earlier with the speeding situation. You have the distance, you have the time, you can calculate the average speed. So average speed is equal to 6.2 miles divided by 32 minutes. We don't like minutes, we want per hour. So you put minutes up there to cancel. 1 hour has 60 minutes. So now minutes are canceled. This is 6.2 miles up there. So you have 6.2 times 60 divided by 32 miles per hour, because now it's everything canceled. So at this point, right, you can take the abacus and just compute this 6.2 times 60 divided by 32, and that gives you 11.625 miles per hour. So what we found is that the average speed of this runner is 11.625. Okay, so now let's think about speed versus time graph. The runner starts at the speed 0 because they're usually at that position, right, crouch down, right, to, I don't know what it's called, whatever it's called, waiting for the shot to be fired so they can start running. Their speed at that point is 0. and then they're going to keep running, and then eventually the race is over and their speed is again 0 on velocity, right? This is a time, so I'll say velocity equals 0 again at the end of the race, right? They run, then might walk a little bit and then stop. But the idea is that the runner will eventually stop. So if we calculated that the average speed somewhere average speed is 11,625, you can see that if this height here is 11.625, then 11 is right underneath. And you can see that the runner had that speed at least twice. Now, the wording at least twice is important because you had to have it minimum 2 times. The runner could have been doing this and having that speed 15 or 20 times or whatever, right? But the trick is that the speed is guaranteed of 11 miles per hour twice because the runner started at 0 speed and ended with the 0 speed, right? So in that case, you have the average speed of 625 tell you that 11 miles per hour was the speed at least twice, achieved speed at least twice. Now, we can go back now to that speeding problem and realize what the average that we got, which was 75 on 60, what that did. Remember, if your average is 75 and you know that your two lows when you were measured were 60 and 60, wouldn't that 90 be on the other side? Because if this was plus 15 to get to 75 and then plus another 15 to get to 90, because you kind of have to average 60 plus 90, right, into 75. Do you see that? So you are not going to get ticketed for 90 because you can't. Maybe you were not driving 90. Maybe you were driving 76 for a very long time, right? But the thing is that we don't know what the top speed was, just like for the runner here. We have no clue what the top speed was. We just know the average speed. And we know that the average speed is definitely lower than the maximum speed because average is in the middle. We know that the slowest speed was 0 at the start and the end of the race, right? So, I don't know, the top speed, 13, 15, 30 miles per hour, I don't know, right? I don't even know what's humanly possible for the fastest running speed. That's probably something you can ask Google, and Google will tell you. But the trick is that we know that at least twice this runner was going 11 miles per hour. So those are the word problems. There are more things. There is another 100-meter speed. And running pace, mean value theorem for linear functions, the police problems again. So, couple of these word problems, not too many, maybe 5 altogether in the book. And that's the mean value theorem. So one more time, studying this formula is not just remembering the formula. I mean, studying the theorem is not just remembering the formula. It's also remembering those two conditions. Because if any of the two conditions fail, your calculation would fail. I did show when the function was not continuous with 1 over x, you can very quickly come up with the same conclusion, right? If you draw, let's say, absolute value of x, which is not differentiable at 0, and put two values like this, right? The function is not differentiable at that spike, so you will not be able to find anywhere to put the slope, right, for the tangent line like this. because all of the slopes are either +1, -1, or 0 at the peak. So there is no slope of, let's say, 2 or 1/2 or whatever else you might come up with. So it is very easy to break this theorem by sneaking in a discontinuity or sneaking in a problem that is not differentiable at the point included in the interval. So just be very careful about that, and if it passes both conditions, then you can just go in and plug everything in the formula and quickly compute. Now for the what you would call the real life problems, well, clearly, right, running and driving and flying the plane, like those are all continuous functions. And then since there is velocity involved, that's a derivative, so it's differentiable everywhere as well. It's not like a velocity fails at some point when you're running from point A to point B, right? You have the velocity constantly. Now, whether it's a slow or fast velocity, that's a different story, but it doesn't fail at any of the points in between. So that's the story of mean value theorem. Let's take a short break. When we come back, a ridiculous title called What Derivative Tells Us, which is, I don't know if they could come up with a worse title. We're going to talk about the first and second derivative test and the properties of the graph that those uncover for the increase, decrease, concavity, and all of that good stuff. So we're finally going to talk about that inflection point. So it's very important section for analysis of graphs and everything else. So we'll be back in 5.